Another important concept on the microscope is the concept of parfocality. When you're looking through a 10x objective and you're in focus and you want to go to another magnification, it's not necessary to lower the focus of the stage. You can be in focus at 10x and go to your 20x or 40x and be within a half a turn of the fine focus. This is called parfocality and is available on most modern microscopes. Let's discuss the concept of resolution. Resolution is the ability of the objective to resolve two separate structures that are separated by each other. The closer the distance between two objects that are not one object, the better the resolving power of the objective. So resolution is the function of the spacing between two separate objects that allow each one to be individually resolved. We're not going to discuss the formulas, but I do have a diagram that shows this. And on this diagram you can see several individual spots and they have halos around them. That's a function of the wave properties of light, but we will not discuss that. But here you see an unresolved structure, so we have two dots that seem to be touching each other. They are unresolved. Here we have two dots that are just about to separate from each other. Again, they're not individually resolved. And here we have several dots that are completely separate from each other, and so each dot is fully resolved in the microscope. Now, most microscopes that are high quality today can resolve features that are about 500 nanometers in size, maybe a little bit better depending on the wavelength of light that you work with. So you can expect to resolve something on the order of 400 to 500 nanometers in your specimen. When we're using light in a microscope, the light can be refracted by the different mediums that it goes through. For example, when light transitions from air to glass, it is refracted or bent based on the density of the glass. So the light is going to be refracted by the cover slip. It's going to be again refracted by the mounting medium that's in around the specimen. It's also going to be refracted by the specimen, and it'll be refracted by the slide itself. If you use immersion fluid between the objective and the cover slip, the light will also be refracted by that immersion fluid. So it's important to remember that light is being bent by everything you're putting it through, and so you must use the proper materials to get the highest resolution out of the objective. One advantage of the confocal microscope is that you can work with fairly thick specimens. The confocal microscope uses a series of pinholes to make what we call optical sections, and so we'll discuss more about that later. But an important concept to understand is the depth of focus of your image and the numerical aperture of the objective. They work together. And so here I have a diagram that shows a low numerical aperture objective with a very large depth of focus. So everything from the top of this blue cone to the bottom of this blue cone is in focus with a low numerical aperture objective. Obviously that means that a lot of information is traveling through the objective, and so it's not highly resolved. When you increase your numerical aperture, not only do you decrease your working distance as we saw before, but also your depth of field or depth of focus decreases. And so less of the image is in focus at one time, but it's at a higher resolution and it's a brighter image.